This is the ultimate engineering challenge, spanning a strait that is vast, incredibly deep, and extremely dangerous. Engineers aren't just fighting gravity here, they are battling wind, waves, and the Earth's crust itself. Forget every bridge you know. These mega projects consume billions of dollars and take decades to complete. But why do we build them? And how exactly do you place a foundation in the deep ocean? Today, we are decoding the impossible art of connecting landmasses that were never meant to touch. First, let's talk about the biggest enemy, distance. These straits are often more than 3 kilometers wide. At this sheer scale, traditional bridge designs would simply collapse under their own massive structural weight. The only solution is a suspension bridge, but not the ordinary kind you see in your city. We need towers taller than the Eiffel Tower just to keep the heavy main cables from sagging. The next major problem lies deep underwater. The seabed in these straits is almost never flat. Engineers must lower massive hollow concrete blocks, known as caissons, to absolutely mind-boggling depths below. Imagine trying to park a 10-story building in a precise spot while strong currents push you. A tiny error at the foundation leads to a catastrophic misalignment of meters at the tower top. To fix this, they use advanced GPS and underwater robots to flatten the seabed before lowering foundations. Once the foundation is set, the real war begins above the water, the battle against the wind. Out in the open strait, wind is unobstructed. It can reach tropical storm speeds at any moment. If designed poorly, aerodynamic flutter will rip the entire bridge apart like a piece of paper. Engineers solve this by shaping the bridge deck like an airplane wing to slice through the wind. They leave gaps between the traffic lanes, allowing the wind to pass through instead of pushing. But wind isn't the only threat. Many straits sit directly on top of active tectonic fault lines. The bridge must be capable of withstanding massive earthquakes without collapsing into the ocean below. The secret lies in massive hydraulic dampers, which act exactly like the shock absorbers on a car. These allow the bridge to sway gently with the rhythm of the earthquake instead of fighting it. Now, let's talk materials. Regular steel would corrode in just a few years in this salty environment. They use advanced dehumidification systems inside the main cables to keep them permanently dry and safe. Each main cable is actually made up of tens of thousands of smaller steel wires bundled together. The total length of these steel wires could wrap around the planet Earth multiple times over. Spinning these cables across the strait is a precise and dangerous mechanical ballet in the sky. A specialized pilot boat pulls the first lead line, paving the way for thousands of tons of steel. Spinning wheels run back and forth for months, weaving the steel backbone of the bridge. But engineering isn't the only barrier. We have to talk about money, a lot of money. These projects frequently go over budget due to unexpected delays and unforeseen geological surprises. Look at the Akashi Kaikyo Bridge in Japan. It was expensive, but has proven its immense value. Or the proposed Messina Bridge in Italy, which remains a dream due to costs and risks. Politics also plays a huge role. A bridge connecting two lands changes the entire geopolitical map. It boosts trade and tourism, but it also creates significant vulnerabilities for national security and defense. So, how does the actual construction happen? It is essentially like assembling a gigantic Lego set. Deck sections are prefabricated on land factories to ensure absolutely perfect quality control. Then, they are shipped by barge to the sea and lifted by massive floating cranes. This is the most dangerous moment. A strong gust could swing the steel block into the tower. Engineers have only a few hours of quiet weather window to execute this critical maneuver. Once the sections are connected, they form a continuous ribbon of steel stretching across the ocean. But the work isn't over. The asphalt must be a special mix so it doesn't crack. The bridge will expand and contract by meters between summer and winter. The road must handle that. Lighting systems are also an art form, serving as aircraft warnings and architectural beauty.
There is a hairline crack just
Maintaining a
above the
monster
slice.
like this is a full-time job that literally never ends. Robots are slowly replacing humans for inspecting cracks in the most dangerous, hard-to-reach places. A successful cross-strait bridge can completely transform the economy of an entire region. It turns isolated islands into bustling logistics hubs and connected economic powerhouses. But what is the cost to nature? We must consider the environmental impact on marine life. Construction noise can severely impact whales and the delicate marine ecosystems nearby. Modern projects now use bubble curtains to dampen the noise and protect underwater life. Looking to the future, we are aiming for even wider, deeper, and more challenging straits. The Strait of Gibraltar, or perhaps even a theoretical transatlantic tunnel concept. New material technologies like carbon fiber could help us build significantly longer bridge spans. Floating bridges, submerged tunnels. The only limit is our imagination and the budget. These bridges stand as a testament to humanity's enduring ambition to conquer nature. They remind us that no distance is too great to be bridged by human ingenuity. From design to finance to construction, it is a symphony of thousands of brilliant minds. Next time you cross a bridge, remember the incredible engineering happening beneath your feet. A silent, constant battle between steel, concrete, and the raw power of the ocean. The art of bridging the strait isn't just construction. It is about connecting humanity. If you enjoyed this dive into extraordinary engineering, please like and subscribe to the channel. Which mega project do you want us to analyze next? Let us know in the comments below.